Alright, welcome back, class. 8.3 is not a real long section. You'll notice that in the homework. However, it does have an algorithm in it that's a tool that's going to be very useful for us. And that's what we're going to start with first. And then I've got a little couple theorems in here that are going to prove useful as we investigate these polynomials. Okay, so ultimately our goal is to be able to find all of the zeros of a polynomial. Okay, sometimes that can be difficult because sometimes the polynomials can't really be factored, and so then how do you find the zeros? Okay, all right, so this first tool that we're going to talk about is something called synthetic division. Okay, you may have heard that before, be familiar with it. It's basically a streamlined way to divide some polynomial, like this one here, by a linear polynomial. Okay, and it's basically a streamlined approach to doing the long division. So if I wanted to divide, let me zoom in here. If I wanted to divide this cubic polynomial right here by this linear polynomial, the result would be a quadratic. It would be a second degree polynomial, and that's what we actually see here. So you can actually do this division using long division. Okay, you say x goes into 4x cubed, 4x squared times, and then you multiply back through. 4x squared times x is 4x cubed. 4x squared times negative 2 is negative 8x squared. And then you subtract, just like with regular division. You bring down the next term, you try to divide again, okay? But you don't actually need the x's to do this process. In fact, if we take the x's out, and you look over here, then you say 1 goes into 4 times. 4 times 1 is 4. 4 times negative 2 is negative 8. And then you subtract. Well, 4 minus 4 is 0. And then negative 3 minus a negative 8 is actually 5. Okay, so we're getting the same numbers that we had over here. And then you divide 1 into 5. That goes 5 times. And 5 times 1 is 5. 5 times negative 2 is negative 10. You subtract again, 5's cancel. 1 minus negative 10 is 11. Bring down your last term, divide one more time, you get 11, and you end up with 23. This is what we refer to as the remainder. Okay? Then you could go back in and add your x's. Since a cubic polynomial divided by a linear polynomial will be a quadratic polynomial, when I add my x's, I'll get 4x squared plus a 5x plus an 11. Okay? Well, the reason I showed you this is because there's an even faster way to do this. Okay? You can leave these numbers right here. These numbers end up being the coefficients of this is called the dividend. Okay? And then, so you can see here, these coefficients or these numbers, I just made a row. Okay, and then you can always use the opposite of this number here. What this does is, when you go through this algorithm for synthetic division, when you're using the opposite of this number, it allows you to look at this instead of subtracting each time, you are adding. Okay, and so it kind of goes like this. I'll show you. So you'll always drop down the first number, 4, and then you start multiplying. Okay, similar to what we were doing up here when we multiplied back through. 2 times 4 gives you 8. Negative 3 plus 8 is 5. 2 times 5 is 10. And 1 plus 10 is 11. 2 times 11 is 22, and 7 plus 22 is 29. Now look, 4, 5, and 11, aren't those the same numbers we got up here? And didn't we get the same remainder, 29? And then you go back and add in your x's. Okay. All right, so that's the way the synthetic division algorithm works. You're going to take the coefficients from whatever your dividend is, okay, and then what you put in this box will always be the opposite of the constant right here in your divisor. So if the divisor is x minus 2, then we're going to use a positive 2. And doing that just allows us, instead of subtracting each of these columns, we can add the columns because we're using the opposite sign. Because that's all subtraction is, right? It's adding the opposite. One other thing, and I think I put this in the notes, make sure that the dividend is in descending order without any missing terms. Okay, so if we come back up here, the dividend is in descending order, and it doesn't have any missing terms. Now if it did, if a term is missing, then you're going to use a 0 for its coefficient. Okay? And then furthermore, the divisor is always going to be the opposite of that constant in the binomial divisor. Okay, so always the opposite of this number here. All right, so let's try one on our own. And we'll get some more practice because we're going to be using synthetic division. All right, example 1. It just says use synthetic division to divide here. So similar to the last one, we've got a cubic polynomial divided by a linear polynomial. And we know the result will be a quadratic polynomial, or a second degree. Because x cubed divided by x squared, or excuse me, x cubed divided by x is x squared. All right. Well, I'm going to use the synthetic division. But I notice that my dividend is in descending order. However, it has a term missing. There's no x term. Okay. So I first rewrite it like this. And then I copy all these coefficients. So 1, -4, 0, and 5. Okay. Draw a bar down here. And then in your little box, or half box, you're going to put the opposite of that constant that's in the divisor. You're going to put 2. Okay, and then this is how it works. You're always going to drop down your first number, and then you're going to start multiplying and adding. So 2 times 1 is 2. -4 times, or not times, but -4 plus 2 is -2. And then 2 times -2 is -4. 0 plus -4 is -4. 2 times -4 is -8. And 5 plus -8 is -3. Okay. So the -3 will be our remainder. Now I just need to come in and add my x's. These are the coefficients of my quotient. Okay. So it'll become 1x squared minus 2x minus 4, and you can say that the remainder is -3. Okay? So that's kind of how this process works. And we'll be using this process some more. We're actually going to use it here in a minute. Because let's look at this next theorem, the remainder theorem. I will read it and then I'll explain it. Okay, it says if a number c is substituted for x in some polynomial, okay, so in other words, if you plug some number in to the polynomial, then the result is the remainder that would be obtained by dividing that polynomial by x minus c. Okay, in other words, plugging c into the function will give you a value of whatever the remainder is if you had done synthetic division. Okay, so for example, if I want to see, well, right here in the notes it says if we want to find f of 2, okay, this theorem is saying that it would be the same as dividing our polynomial, okay, whatever that is, by x minus 2, and then the remainder would be the answer for f of 2. Okay, so really what this is telling us is that if I do synthetic division with 2, the remainder will be the actual function value. And so this offers us another way to evaluate a function, a polynomial anyway. Okay, and we'll talk about why you might be interested in this here in a minute. Okay, so yeah, the remainder theorem offers us another way to evaluate a polynomial. Okay, for example, if we want to find f of 2, we could plug 2 into the function the way we've always done, or we can use synthetic division with 2, and the remainder will be the function value. The reason synthetic division is a good tool for evaluating functions, guys, is because depending on the complexity of the, well, when I say function, I mean polynomials. Depending on the complexity of the polynomial, using synthetic division to evaluate it can drastically reduce the number of operations required. Okay. And then furthermore, it also gives us a quotient. And we'll talk more about that here in a minute, okay, why that might be useful. But let's use synthetic division to find the function values for this particular polynomial. And then we're going to check our work using a graphing calculator, using a calculator, okay? Or at least check one of these. Alright, so if we want to find f of 2, I can do it, I could just plug 2 into the function, that would be one way, but I'm going to do it using synthetic division. So I'm going to make sure that my polynomial is in descending order, which it is. There are no missing terms, so I'm going to go ahead and write or copy a row of those coefficients, 1, negative 14, 59, and negative 70. Okay. And inside my box, I'll put a 2. And I'm going to repeat that same algorithm. You're going to drop down your 1, and then you're going to start multiplying and adding. 2 times 1 is 2. Negative 14 plus 2 is negative 12. 2 times negative 12 is negative 24. 59 minus 24 is 35, I believe. And 2 times 35 is 70. Negative 70 plus 70 is 0. So this means that f of 2 is equal to 0. Okay, so the function value when x is 2 is 0. So this actually verifies that 2 is a 0 of this polynomial. And so if we were to graph this polynomial here, we would see it probably cross the x-axis at 2. Because I'm guessing 2 just has a multiplicity of 1. Okay, we'll graph it here in a second. Alright, now let's evaluate the function when when x is negative 5. So, I do it the same way, using synthetic division. Okay, drop down my 1. Negative 5 times 1 is negative 5. Negative 14 plus negative 5 is negative 19. Negative 5 times negative 19 is actually 95. 59 and 95 is, I think, 154, I believe. And negative 5 times 154, what is that? I want going to say that it's negative 770. We'll check this one. And then negative 70 plus a negative 770 will give us a negative 840, okay, if I'm correct. So then this means that whenever x is negative 5, the y coordinate, or the function value, is negative 840. Let's actually check this one in the calculator. Okay. Oops. Alright, so I'll just plug negative 5 in for those x's, so I want to make sure I keep it in parentheses. I'll cube it. Minus 14 times negative 5, and that is squared, plus 59 times negative 5, and then finally minus 70. And hit enter. Oh, and it is negative 840, so we did the arithmetic correct. Okay, and you get evidence that this remainder theorem is actually true. Okay. Alright, we'll do the last one. F of 7. So what's the function value when x is 7? Well, I'll do it the same way using synthetic division. Drop down my 1. 7 times 1 is 7. Negative 14 plus 7 is negative 7. 7 times negative 7 is negative 49. 59 plus negative 49 is 10. 7 times 10 is 70. And we get 0 again. Okay? So this means that 7 is actually another 0 of this function. And that's really how we're going to be using synthetic division. It's going to be a quick way for us to determine whether a number is a 0 or not. And then we're going to work with the quotient that's left. Because if it is a 0, then this quotient that's left over, this quadratic quotient right here, this will be a factor. And then if we could factor that, we might be able to find the other two zeros of the function. Okay. What I want to do real quick, though, is just show you in Desmos, let's see, x cubed minus 14x squared plus 59x. Here's minus 70. Okay. And look, guys, this verifies. Where do we see the function cross or touch the x-axis? At 2, which was a 0, and at 7, which was a 0, and then evidently 5 is also a 0 of this polynomial. Okay, it's a third-degree polynomial, so it should have 3 zeros. All this remainder theorem tells us, though, is that using synthetic division is just another way that we can evaluate a polynomial. Okay. Alright. I'm going to try to finish this up in just one video. Okay. I'm going to give you one last theorem, and it's called the factor theorem. This is the results of this theorem I think you may already know intuitively, but I want to show you something here in Desmos. A little activity. Okay. So the roots for the parabola, so a root is just another name for a 0 or an x-intercept. So it says drag point A to move the parabola such that its roots are the two open blue dots. Okay, right here. So I'm going to grab that parabola and I'm going to move it, and let's see, right up, I'm close, not quite though, right there, okay, right there. And so you can see And this parabola has roots of 2 and 6. Or in other words, it has zeros of 2 and 6. Okay? Let's go to the next slide. And the parabola that's described, since the zeros are 2 and 6, the factors are x minus 2 and x minus 6. Okay? So what this is showing us, and probably what you already know by now, is that the factors of a polynomial are related to the zeros. In fact, that's how we find the zeros, right? That's how we've been finding them. We've factored the polynomial, and we've set the factors equal to 0, and from each factor, there corresponds a 0. Okay, so that's basically what the factor theorem says here in the notes. See, it says if f of c is equal to 0, then x minus c is a factor. That just means that if 2 is a 0 of your polynomial, then x minus 2 is a factor. Okay. And let's go back to this real quick. What about this one? Okay. So it says, use what you noticed on the last screen to write a function for the parabola whose roots are at the two open blue points. So let's pretend this parabola was crossing the x-axis at these two values, 4 and 7. So then my polynomial would be x in factored form, x minus 4 times x minus 7. Okay? So these two factors correspond to these two zeros. And it puts it right there. Okay? And then the same thing here for this one. Okay? So the reason I'm showing you that is just to show you that we've dealt with this before. Okay, the factor theorem tells us that if we can find the zero of the function, then we can find the factor, and vice versa. In fact, we've done this. Think about a quadratic function. If we were asked to find the zeros, one way we could do it would be to factor it, so it would factor like this, and then we would set those factors equal to 0, and we would get negative 2, which corresponds to this factor, and negative 3, which corresponds to this factor here. Okay? So that's all the factor theorem is telling us. But it also allows us to work backwards. If we know that the zeros of a function or a polynomial are negative 2 and negative 3, then we also know that the factors that build or make up that polynomial have to be x plus 2 times x plus 3. Okay? And in the next section, we're actually going to use that fact. We're going to be given the zeros of some polynomial, and we're going to have to construct the polynomial. Similar to the way I just did in Desmos, you start off by finding the corresponding factors, and once you know the factors, you can multiply those together, and that'll give you the polynomial in standard form. Okay. All right, well, let's look at this last example. It says, using synthetic division, determine whether the numbers are zeros of the polynomial. Okay. Well, we sort of already did this in the previous example. We wanted to determine whether 2 and negative 1 are zeros. Well, one way we could do it is just graph. You just graph this polynomial to see if they're zeros. Okay, but we're actually going to use synthetic division. Make sure it's in descending order, which it is. There are no missing terms, because guys, if there are missing terms, it is crucial that you use zeros for the coefficients of those missing terms. But in this case, there aren't any. So my coefficients are 1, negative 6, 1, 24, and negative 20. And make sure you're careful to carry those negatives with those numbers. So we're going to see if 2 is a 0 first. Okay. So same procedure. 2 times 1 is 2. Negative 6 plus 2 is negative 4. 2 times negative 4 is negative 8. 1 plus negative 8 is negative 7. 2 times negative 7 is negative 14. 24 minus 14 is 10, and 2 times 10 is 20. So we do get a 0. The remainder theorem tells us that because we get a remainder of 0, then this function is actually g. It tells us that g of 2 is equal to 0, or in other words, that 2 is a 0. Okay? So if you were to graph this function, this polynomial, it will at least touch or cross one of the two, the x-axis at 2. Okay? Now let's see if negative 1 is a 0. So I'll do the same thing. Okay, so I'll start multiplying and adding. Negative 1 times 1 is negative 1. That'll give me negative 7. Negative 1 times negative 7 is positive 7. And 1 and 7 is 8. Negative 1 times 8 is negative 8. 24 minus 8 is 16. But here, negative 1 times 16 is negative 16. We're not going to get 0. We're going to get negative 34. Okay? So all this tells me is that negative 1 is not a 0. Okay? And then if you wanted, you could graph this polynomial. I'll leave that to you guys. But when you do graph it, it will probably cross it at 2. Because I think 2 will probably have a multiplicity of 1. Okay. But anyway, we're going to be using what we've learned from 8.3 in section 8.4. Okay. Alright, so I will see you there.